All right, welcome to this explainer. Today, we're diving into a really high-stakes mathematical mystery, and it's a mystery that actually takes place entirely inside the fiery, completely chaotic heart of solid rocket motors. We're going to explore how incredibly tiny, literally microscopic events can scale all the way up to threaten some of the most massive, powerful machines humanity has ever built. I want you to picture this scenario for a second because it's pretty wild. Imagine the sheer roar of a rocket, the intense sound waves just echoing inside the engine chamber itself, actually starting to dictate the behavior of millions of microscopic flames. It creates this terrifying, destructive feedback loop. Basically, the sound changes the flame, right? Then the flame releases heat that amplifies the sound, and suddenly you've got a rocket literally tearing itself apart from the inside out. So how on earth does this happen? And maybe more importantly, how do we stop it? Okay, Section 1. The aluminum power boost. Well, to really grasp the problem, we first have to understand the fuel. You see, engineers add aluminum to solid propellants because, when ignited, these microscopic aluminum droplets melt and burn. They effectively act as millions of tiny little engines. And these tiny engines absolutely massively increase the overall thrust of the rocket. But here's the catch. They don't just burn nicely like a standard log on a campfire. They're actually releasing heat as they get completely swept up and carried away by the intense gas flows inside the rocket chamber. Now take a look at exactly where this combustion is happening. If you look at the motor chamber here, you'll see the solid propellant sitting up at the top. And right below it, that thin red strip, that is the aluminum combustion zone. It's a highly concentrated, incredibly volatile layer sitting right on the boundary of the solid propellant. All those millions of microscopic droplet engines we just talked about, they're igniting and burning out completely within that tiny red margin before they flow down toward the nozzle. Moving right along to Section 2, the acoustic instability mystery. So packing all that concentrated power into one space comes with a seriously huge risk, and it's called thermoacoustic instability. It sounds complicated, but simply put, it's a destructive dance between sound waves and heat. Small pressure oscillations, which, are basically just sound waves, travel through the rocket chamber. And if these sound waves happen to perfectly synchronize with the heat being released by our burning aluminum droplets, the vibrations start to amplify. If that goes unchecked, this feedback loop triggers massive thrust oscillations that can physically tear apart multi-million-dollar rockets. And this isn't just some theoretical lab problem. It's a very real known threat to major aerospace programs like the Ariane 5 and Ariane 6. To figure out how to stop this, researchers really had to play detective, and they managed to pin down two main clues, or sources, for exactly why this heat release fluctuates and syncs up with the sound. First, you have what's called the volumetric contribution. All this means is the sound waves are actually changing how fast the droplets evaporate throughout the entire cloud. Second is the boundary contribution, and this one is much wilder. It's an aggressive physical flapping motion that happens right at the very edge of where the cloud finishes burning. Just look at the staggering difference here. On the left, we've got the unforced heat release, and on the right is the forced simulation. Under acoustic pressure, the heat release just fluctuates wildly, especially in those really concentrated bands. This also highlights the Rayleigh index, which is just a way to measure how heat actively drives acoustic waves. See those deep red zones? Those are the specific spots where unsteady combustion is actively churning out dangerous sound waves, just feeding right back into that destructive cycle. All right, Section 3, flapping flames and fluctuations. Let's zoom in a bit on the boundary of our microscopic flames across an acoustic cycle. Focus your attention right on the bottom edge of that bright red-orange zone. You can clearly see this really aggressive, rhythmic flapping motion at the end of the combustion zone. But what's incredibly strange about this is that the flapping motion is happening radially, meaning up and down on this chart. That's super weird because the acoustic waves bouncing around the chamber are mostly moving axially, so left to right. So why in the world is it behaving so erratically? Well, check out this zigzagging blue line, which represents the acoustic boundary layer. Because gas is being ejected so rapidly from the solid propellant surface, when the acoustic waves interact with the wall, they create these super complex, intense vorticity waves. Basically, this means right where our microscopic aluminum droplets are trying to burn, up in that red zone at the top, the gas velocity is just rapidly oscillating back and forth. The droplets are constantly being pushed and pulled around by these chaotic velocity fluctuations. Which brings us to Section 4, fixing the mathematical model, the climax of our detective story.
For years and years, the mathematical models that engineers relied on simply did not match the violent reality of what was happening inside these engines. The old model, developed by Gallier and Godefroy, assumed that the heat fluctuations were solely caused by changes in the droplet speed. It basically thought, okay, the sound pushes the droplet faster, so it burns differently. Makes sense, right? Simple enough. But the new mathematical model proves this is completely missing the full picture. We absolutely must account for droplet diameter fluctuations. We have to mathematically model the fact that these little droplets are rapidly shrinking. The flow is actively changing their diameter and totally oscillating their overall lifetime.
And the definitive mathematical proof is right here. This is the smoking gun. Look at the solid black line. That's the raw data from the incredibly complex computational fluid dynamics simulation. Do you notice that massive, sharp spike over on the right side? That represents the intense heat fluctuation right at the boundary where those flames are flapping. Now look at the dashed line, which represents the old Gaylor and Godfrey model. It just falls completely flat. It entirely failed to predict that massive spike in the danger zone simply because it ignored the changing diameter of the shrinking droplets.
So the ultimate takeaway here is super clear. Droplet lifetime oscillations are the key missing variable. Because the sound waves change the evaporation rate, the droplets don't just burn a little differently, they literally run out of fuel and die out at completely different times and locations in the flow. By finally adding this missing variable of droplet diameter fluctuations into the math, the new model perfectly aligns with reality. It successfully predicts that catastrophic boundary flapping motion.
To sum up this incredible breakthrough, we can just look at the researchers' own words. They note that the derived expressions yield a better understanding of heat release disturbances and can be used to predict the stability of a solid rocket motor at reduced computational costs. So what does this actually mean for the real world? It means engineers don't have to tie up expensive supercomputers for months on end just to simulate a single rocket engine anymore. They now have a much cheaper, highly accurate, elegant mathematical tool to flag and prevent these destructive vibrations long before a physical rocket is ever even built.
It's honestly just fascinating. By carefully tracking the microscopic lifespan of a single tiny droplet of burning aluminum, we can actually stabilize a machine that weighs hundreds of tons. It leaves us with a pretty profound thought to chew on. If mastering the math of microscopic droplets can save a massive rocket launch today, how will this exact type of relentless mathematical precision guide our multi-million-dollar missions to Mars tomorrow? Thanks so much for joining me on this explainer. Until next time, keep looking for the big answers hidden inside the smallest details.